who is Professor Jinqiao Duan from the Department of Physics and Mathematics at the Great Bay University. And Jinqiao, please, if you want to talk about critical transition and stochastic dynamics. Thank you.
Thank you very much, everybody. Thank you. It's my pleasure to speak here again after 16 years. So this is about critical transitions tied to our workshop's theme, and also relevant to the people from the other program. So this will involve some connecting orbits. This is a concept in deterministic dynamic systems as well. Transition paths used in dynamic, stochastic dynamic systems, also in statistical mechanics. Schrödinger bridge, the Schrödinger is that guy from quantum mechanics, but it's related to the transition as well. So this is partially coming from this upcoming book by Schrödinger, collaborator Ting Gao, Wuhan, China, Qiao Huang, Nanjing, China, Yuanfei Huang, South Korea. It's about geometric methods for stochastic dynamic systems. So our story is about Schrödinger bridges as connecting orbits or transition paths for stochastic systems, and that carry information for critical transitions. And critical transitions for me, for these presentations, for those are those abrupt switch or shift from one dynamic regime to another, often irreversibly. So in this presentation, the connecting orbits and critical transitions are sort of linked together. And critical transitions are coming out of the context of multi-stability and meta-stability. And these related activities have been going on at least for the last 10 years that I have started to pay attention. And books are coming out, and some old, some new, and even this one about collapsing of meta-stability. So let's recall transitions in nonlinear deterministic dynamic systems. This is a damped pendulum. And as soon as you turn on the damping, when gamma becomes positive, even though when it is very small, we see the parameter propagation-induced transition. That has been talked a lot in this program. Okay, but I'd like to point to you. So this we have a stable, unstable manifold for one equilibrium point connects or coincide partially with the stable manifold of the other steady state. Okay, the green one. So that is the connecting orbit or heterokinetic orbit. This is largely talked about, largely discussed in the dynamic systems group at Cornell University, Guggenheim Holmes, and some of you come from that group, including myself. Now look at this connecting orbit, the green one. It has a direction. It goes from one steady state to another. It goes one regime to another. Now this transition time or connecting time is, how long is the time? How long is the transition time? Infinite. Otherwise, it will violate the uniqueness in the existence for ordinary differential equations. So remember, transition time is infinity. It's too long for us, right? Okay, so another second observation is, if you look at that green curve, the nearby orbits, nearby points, will sort of follow it to go from a neighborhood of one dynamic regime to the neighborhood of the second one. So that means this connecting orbit really is an organizing machinery. It tells us about the transition, right? So once you know this connecting orbit, you pretty much know what's going on for this system, and for many other deterministic systems as well. So heterokinetic orbits are very important in organizing nonlinear dynamics. And in our today's context, it also carries information for transition and the tipping, critical transition and the tipping. So this is the whole thesis for this presentation. I bet is in the context of stochastic dynamic systems. I hope to share you my excitement for this work, and I'd like to get your feedback from you, and during this month, and then we can get something new out of it. What do you think? Okay, so. This connecting orbits have been studied in Hamiltonian systems for a long time. Yeah, this is interesting. And the people know these are important. They know, although they don't talk about the transitions, but they know the organized dynamics and the chaotic dynamics as well. In infinite dimensional systems, we have some people working in the context of infinite dimensional PDE dynamic systems. This is also pretty much the same story. They are connecting orbits, goes from a steady state to another steady state. It also organizes transitions, but in an infinite dimensional space. Okay, the transition time is also infinity. Okay, and in fact, there is a infinite dimensional version of Poincare-Bendixson theorem, which says about the importance of connecting orbits or heterokinetic orbits. So let's summarize. In deterministic systems, nonlinear, these connecting orbits are important. Transition time is infinity. There are no transitions within finite time horizon. Okay. And they connect two invariant sets. I mean, there's stable, unstable manifold for one and the stable manifold for the other. They touch each other. Okay. Okay. And if the system is non-autonomous, usually you will see this kind of things in the sectional dynamics, such as Poincare section. Okay. But the transition time is infinity. Otherwise, it violates the existence and the uniqueness. Okay, and connecting orbits carry information for transitions, especially for critical transitions. That's why we like to talk about this, and I like to show you one case that will do our trick. Now, in climate system, ecological system that we have been talking about in a program at Newton Institute for this month. And also biophysical, biomedical, especially the green systems. The transition time is finite, and it's often very short. Otherwise, we don't worry much, right? If it's like people in geoscience, they may worry about it if it's very long, but it's often very short. Even for geoscience, it's very short compared with our geological time scale. So anyway, it's short, finite. So that means what we have been talking about in the framework won't work very well. I like a statement by Yuri Manning, a mathematician. He said mathematical modeling is a metaphor. Okay, you use the mathematical models as a metaphor to decipher something that you observe in science and engineering. So you can use deterministic or non-autonomous systems to deal with tipping phenomena, critical transition. But I personally, I like to use the stochastic systems to decipher or quantify something in critical transitions. Hopefully, we can do something different, and then we can combine to do something together to do great things. Okay, so there's a need for finite time connecting orbits, right? Some of you talked about, geology and Gary, you talked about finite time and Lyapunov exponents, and finite time and coherent sets, right? So this makes a good connection with that as well. And this finite time connecting orbits are very common in biomedical systems. Often time scales much shorter than in climate or geophysical systems, especially in my current interest in brain science. So this multi-stability, metastability are very important issues. So this is an example for Alzheimer's disease. It's unfortunate. Some of the people in our community, when they right past 80 years old, and they had this problem, some of our friends and the teachers. So this really motivates us to look at the AD, Alzheimer's disease, a brain disorder. It becomes common. One reason is because people live longer. So this MRI or fMRI image shows the left one is healthy brain. Like right one is disease brain. And there are many data sets for this. Say NSI in Germany and some other data sets in UK, China, in other places. You can find these pictures. And even with naked eyes, you can see clear differences. Often, this disease is started 10 or even 20 years back. So if we can catch something during that time period and to do something for early warning or early intervention, although we don't have good medicine for this time, but maybe we can do something, or maybe we can provide something useful. So this is final time. This is only, I think it's only for 7 years time scale, and you see the differences. The medical doctors can easily see the differences, but not for us. But we like to do something for early warning of tipping, early warning of a critical transition. Say something if we can do something. So we need an indicator, just like our thermometer. And for thermometer, the tipping point is 37.5. So can we have something like that, a scalar quantity that gives us a computable tool. By computing it, we can see, wow, something might be going on. Because we have many data available, and machine learning tools, AI community are attacking this issue. And they also need good mathematical tools in addition to correlation variance analysis. So this is a part of the thesis for this presentation and the motivation. So we did a finite time collecting orbits. Okay, and I mentioned that I like to use stochastic dynamic systems as my mathematical metaphor for dealing with critical transitions for systems and random influences. A system regime needs, in deterministic transition, we talk about invariant set to invariant set to another invariant set. But here we don't have to. We could look at the set that may not be invariant, but still important. The transitions out of it or into it are the things that we like to deal with. Okay, remember, connecting orbits is the key concept from dynamic systems. That's what we like to use to gauge into the critical transitions. Okay. Now in the quantum, in the magazine Quantum that you probably received in your email last week, there is an article about connecting orbits to try to connect, or I think it's called connecting trajectory, to make a connection or link between gravity and the quantum mechanics. It's a good article. So it links to my presentations here in that way. Okay, so what we are going to do is medical imaging. I mean, you see those two-dimensional things, right? We in the data analysis, we treat this as a probability distribution. So we look at the densities, probability densities for each medical image. Now that means what? That means we are not doing sample path analysis. Instead, we are going to live in a higher infinite dimensional space of probability densities. Now we pay the price. This is infinite dimensional, but we also gain something. It's deterministic, no uncertainty in that space. It carries uncertainty information inside it, but on the surface is deterministic. People don't like uncertainty. So we gained something, we lost something. And we also gained one thing. In that space, the probability evolution is linear. Even though your underlying stochastic dynamics is highly nonlinear. So we lived to a higher dimensional space, we gained something, we lost something. So in this space, a system regime, we just mean a probability density, one image to a lot of image. Okay, the transition means a connecting orbit the infinite dimensional space of probability distributions. Now, in the space of probability densities, what can you add them together? Can you add two densities to get another density? No, we cannot. So it's not a linear space. So it can never be a Banach space. It's a metric space alone. So that's why there's a lot of things going on, analysis in metric space. Now this space has many distances. For example, Puyol-Holm distance and the total variance distance and those other things. And I counted there are 23 of them. Okay. But there's one that gives us more mathematical tools. That is the Weissenstein metric, Weissenstein distance. So this is related to the autocalculus. That distance gives us a lot of more things to do. In fact, we have a sort of at least a weak Riemannian structure. So therefore, with the Riemannian structure, we can do more things. Although it's not a linear space. So that's why we talk about a Weissenstein space. Some people call it a Weissenstein manifold, but actually it's not yet a Riemannian manifold because the Riemannian structure is only weakly defined at this time. Okay, but it's infinite dimensional because it's not finite dimensional. Okay, so now remember we are always talking about a connecting orbit. So this in the Weissenstein space, everything is deterministic. So the connecting orbit, we'd like to find the ones which carries important information, right? It carries important information. What do you mean important? Okay, it often means minimizing something by following a physical principle, Hamilton's principle, Lagrangian principle. And for example, this one follows a Hamilton's principle by minimizing the relative entropy. Mathematicians, entropy has a different sign than physicists. So that's why we talk about minimizing rather than maximizing. Okay, so by minimizing relative entropy, we have a curve connecting two probability densities. And then in 1980s, and the people realized, wow, this is something that Schrödinger talked about in 1930s. Okay, when he was trying to develop a thought experiment in the hope to better understand quantum mechanics. So he was looking at a group of particles moving to and observed them 1 hour later. So they have two group of particles. Of course, they changed, but we can treat each as probability densities. So his question was, what is the most likely path to go from one distribution to another? So that's why we call it Schrödinger bridge. Otherwise, the better name would be connecting orbit. Okay, so this becomes a deterministic calculus of variations and optimal control problem, because with the initial and the terminal constraint, you want to go from one to another. Now, just to quickly remind you, for people with a stochastic background, probability density evolves by following Fock-Planck equation, which is a linear equation. You can think it's a straight line. So, but we want to, so it will never, usually it will not go from one probability distribution to another given one, because it will go straight, right? So that's why you need a optimal control to push it down to the second target. So it becomes a deterministic optimal control. And that's why Hamilton-Jacobi equation, Fock-Planck equations all get into play. Now in this picture, this shows I put this distribution vertically. So this looks like a Gaussian. So this is 1 pound, but 1 hour later, it has 2 pounds. So this is the evolution. So we can treat this as if there is an underlying driving stochastic differential equation to do the trick. But in the space of, in the Weissenstein space, we will only look at the density, probability density evolution. Okay, so this is a symbolic picture to indicate that. So let's see what we have learned so far. we look at finite time connecting orbits in stochastic systems, connecting two probability densities. It's going to be a curve. Well, in the sample space, there will be many sample paths, but in the Wasserstein space of probability densities, it will be just a curve, just like the curve that you saw for the simple damped pendulum. I bet here the space is infinite dimensional, okay? And we still hope this curve will carry critical transition information, right? Because a curve like that did the same trick for the simple pendulum, okay? And here we have more reason for belief that, because this Schrödinger bridge actually follows a physical law, maximal entropy principle, okay? Yeah. So we are going to get the Schrödinger bridge, which is a deterministic curve in Wasserstein space of probability densities. By examining that curve, we like to gain some information about critical transition and maybe even tipping point. Okay, so that's what we're going to do for the rest of the presentation. Okay. So my metaphor is, mathematical metaphor is a stochastic system with the Brownian noise and the Leffe noise, Gaussian and Gaussian. This has been going on for a while in our program here. But let me remind this to some other people who are not familiar with. And this noise-induced transitions have been going on at least at the latest since 1980s. And more recently, this has been talked a lot in the brain disorder situation. Yeah, and this is a recent work of this year by Yu and his colleagues at NYU about real transitions in lousy hydrokinetic networks. It's a very interesting theoretical work. Brownian motion is for Gaussian noise, and in the same family, we have alpha stable Leffe motion, we just call it a Leffe motion, indexed by alpha. So alpha is between 0 and 2. It's something similar to Brownian motion, except the distribution is not Gaussian. So it's a non-Gaussian process, and it's for modeling non-Gaussian noise. Now the sample paths are not continuous, so this is unlike Brownian motion. But the sample paths for Leffe motion, for the alpha stable Leffe motion, are stochastically continuous. So the continuous in the stochastic limit, okay? So this continuity is weaker than the deterministic continuity, but it allows jumps. The jumps will be modeled by the jump measure, okay? So the jump measure tells us how often and how large the jumps are, okay? This jump measure will come out in the generator. And I said this is a family because when alpha goes to 2, we cover the Brownian motion. So that means this family of stochastic processes really should be considered together. Indeed, this is what people in stochastic dynamics already know. The Leffe-Ito decomposition theorem says if you want to include white noise, then the white noise in a large family is the linear combination of Brownian motion and Leffe motion. When there are no Leffe motion, this is what we often know better, and this is what people call diffusion. And that's the jump diffusion because this guy has jumps. Okay, so this is like what people in deterministic dynamic systems x dot equals if. This is that thing, but in a stochastic setting. Now, there's something called generators, very important. Okay, for the stochastic processes or as solutions, okay, as solutions, there are sample paths, okay? So individual paths won't tell you much. So that's why you need to have some coarse graining. One coarse graining proposed by Markov or his contemporaries is to do the mean observation evolution. And that's called the Markov process. So mean observation evolution. So we have a observable function or measurable function u, then we take the mean. That mean I have a Ex. It is because it's a conditional mean depending on your initial starting point for your process xt at a little x. Okay, so this is the so-called Markov group. If t is positive, we call it a semi-group. And then we have what? Then we have a generator. So this is a deterministic semi-group. Now the generator is a one-dimensional information, is a linear approximation. But when you do the linear approximation for the stochastic processes, after you do the mean observation evolution, you get a second-order operator. And this is something in stochastic. This is something different between stochastic calculus and the deterministic calculus. In deterministic calculus, you take one derivative, that's first order, no problem. But in stochastic calculus, when you take a derivative, the Ito derivative will really translate into second order derivative. Okay, so that's why we have a second order derivative here. And this second order derivative comes from that Brownian motion. So Brownian motion is Laplacian. And after stable level motion gives us the fractional Laplacian. Actually, fractional Laplacian, actually, if you use the Fourier analysis, is actually a singular operator, a singular integral operator. So it's a singular it's an integral operator, therefore we call it non-local. It's fractional. Now, this is a sort of a linear approximation for the mean observation evolution for stochastic system. And it gives us a second order information. Certainly, it should carry macroscopic information for the microscopic evolution because we did the mean. Well, that's once you have the operator, you can use functional analysis. Okay, so this Newell operator is what we already know for the deterministic dynamic system. You use the linear operator. This is as well with the operator group people here. Okay, so this is three components are corresponding to the one-dimensional. Linear approximation of the mean observation evolution for the stochastic system. Now, Fock-Planck equation, what is also called the Kolmogorov forward equation, is for the evolution of the probability density of the solution object, solution paths. It's a linear equation involving the adjoint of the generator. Okay, now this is equation linear. Well, we should get something good in return, right? Because we go from stochastic to finite dimension to infinite dimension, we pay the bigger price. We don't have linear algebra. We expect something good in return, right? What is that thing good? Linear evolution. Okay. Now the backward equation, what's the backward equation? I did not write what phi is. The backward equation by Kolmogorov, this was all developed in 1930s, 40s. So the backward equation, this phi, what is phi? Phi is this guy. Is this mean observation evolution? Okay. So for the mean and for the density, we have linear evolution equations. So hopefully this will be useful for our understanding of critical transition or connecting orbits. So that's what we're going to do. So I hope you could guess out that these things will be useful for examining Schrödinger bridges, right? For the connecting orbits. Do well. But I like to point to the metaphor. Non-Gaussianality to me is non-Gaussianality, non-locality at the level of the evolution, at the level of generators. Okay. I like to, people in this program at Newton Institute, people ask about why do we care about the non-Gaussian fat tails? Also, physicists talk about that a lot. some mathematicians will wonder, if not doubt. Okay. So I like to make a small side track to show you what I know about the impact of noise, comparing Gaussian and non-Gaussian. This is what Gemini did for me. I dictated what I know, and he did that for me. So SDE with Gaussian noise, Brownian motion, or SDE with Levy non-Gaussian noise. Okay, so these are the two systems, Gaussian and non-Gaussian noise, and we talk about properties. So the governing operator is a generator that we talked about. It's the linear approximation of the mean observation evolution. Okay, so now the generator for SDE with Gaussian noise is a local generator, just Laplacian, together with the Newell operator. But we usually don't say that. We worry more about the noise. So it's Laplacian. Laplacian is a derivative, so it's local. And with Levy noise, alpha stable, it's the fractional Laplacian. It's an integral operator, so it's non-local. So you see at the functional analysis part, you already see the difference already clearly. So if you do functional analysis, that also gives you a lot of things to do. That's why there are non-local PDE people working a lot on those kind of things. Now the solution density for the Gaussian noise, the solution density, probability density, it will decay to zero at infinity, right? Because the integral will give us 1. So that says it must go very quickly at infinity, otherwise it won't be the probability density. But the problem is how fast it approaches 0 at infinity. For the Gaussian noise driven SDE, the solution's probability density is going to decay exponentially. But for the Levy, alpha stable Levy, it only drops polynomially. And this was already mentioned in Mikhail Pavliovich's work 20 years back. Okay. Now the mean exit time, this becomes this is about the dynamics now, or statistical physics now. So you look at the bounded domain, and then you run the stochastic machine. The question is, what is the mean exit time it will force to get out of it? It will always be finite because you work on a bounded domain. It will always be finite, but how finite? If noise is small, we have asymptotics. This was also presented in a talk by Lavisa and also Yu Zhou. Okay, so this this exit time when noise is very small, the time is very long. When noise is 0, it may stay there, right? So, but if Gaussian noise, the exit time is long, it's very big, because it's exponential in 1 over epsilon. Epsilon is tiny, so it's a very big number. But it's big. But the Levy noise, it has jumps, so the exit time is faster, although still very long, but it's shorter. So you'll see the difference clearly here. That's for small noise, but for big noise, we don't have a good theoretical results. But the computer can also do something. And then the mechanism for escape is sort of different. Okay. Now I'd like to show you in this side track is the escape probability is very closely related to commuter function that has been discussed in this program at Newton Institute. So escape probability or commuter function. Now in the Levy and Gaussian and non-Gaussian case, they also show linearity and non-linearity. So let me show you quickly. So commuter function you are more familiar with, or escape probability, it solves a deterministic non-local partial differential equation. Okay, so this means you start your particles in a domain D, a bounded domain, and then the question is, what is the likelihood it will land in a domain U, which is outside the domain D? What is the likelihood? What is the probability? Commuter function is slightly different from this, but it's closely related. So the escape probability, and if the probability is 50%, then that's the tipping point, right? So that means the escape probability is also a well-event indicator for early warning. So, so let's look at this. Let's look at this. I need to hurry up. Yeah. So if I only look at the Brownian motion again, low vector field, and for particles starting from -2 to 2 and gets out of the domain to the right. Okay, what's the likelihood? Of course, if the particle is already close to the boundary, the likelihood will be higher for Brownian motion. And then, but the trick point is a linear function here. It's a linear function here. This can be solved analytically. It's a linear function. And now for the left field motion, without the vector field, only look at the alpha stable left field motion, and you ask the likelihood that the particles go from -1 dimensional, -2 to 2, and it gets out of 2. What do you see? For different alpha. Alpha is the non-Gaussianity index. When alpha is approaches to 2, we get the Brownian motion. So when alpha is approach to 2, we get something closer to the straight line. Now what do you see here? How would you summarize what you observed? That's what we call Brownian noise is linear. Non-Gaussian noise is non-linear. This is my metaphor for this. Okay. So you see this not only at the analytical level, but also at the dynamical level, you see clear difference between the Gaussian and non-Gaussian noises. Okay. And if you put the vector field, the nonlinearity into play, that means you have interaction of nonlinearity and non-Gaussianity, and then uncertainty, interaction of nonlinearity and uncertainty. Then you see more interesting dynamic evolution, and that gives us trouble. That gives us more difficulty in understanding critical transition or early warning of tipping point. But that's what we're set to do. Yeah.
Like to ask you something.
Yeah.
So for the Brownian motion, you're talking about a commuter function. So it's basically just harmonic solutions, right?
Basically, harmonic function. Yeah. Yes. Commuter, you need 2 sets, but here I only have 1 set. So it's yeah.
So it's just Laplacian equal to 0, and then you have a,
yeah,
and then the other one has
1 is 0, 1 is 1. Yeah.
1 is 1. So
One is one.
The one doesn't have to be connected, or does it have to be?
1 is on the boundary. Yeah, we talk about an open interval. So 1 is on the board, on the boundary.
Okay.
Yeah.
Okay, so it has to be that. Okay.
Yeah. So it's amazing, right? Very interesting. So it's a straight line. But whenever you start to look at a non-Gaussian, it's not a straight line.
Here's the questions.
Yeah.
So you're talking about medical imaging as a probability density. So probability density of X. So what is that X that you're gonna do on that?
Okay. So for the image, we look at the 2-dimensional. So X will be X1, X2. Okay. So in that case, will be the pixels. Yeah, basically related to pixels. Yeah. There are many programs which turn a data cloud into probability densities. Yeah. Okay. 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 So so summarize this Gaussianity in some sense is linearity or locality. Non-Gaussianity is non-linearity, non-locality. Okay. So that means hopefully, or we expect this non-Gaussianity will have an impact for critical transitions, and also influence our existing tipping points and early warning strategies. Maybe for ecology as well. Okay. Okay. So now after this sidetrack, let's back to our main road. I still like to do the Schrödinger bridge as a connecting orbit, and as they carry information for critical transition. So I like to examine the Schrödinger bridge and define an indicator for tipping. I need to get a part. Yeah. Okay. So that means we find in a Wasserstein space of probability density space densities. We like to find a deterministic connecting orbit. Okay, connecting probability 1, probability density 1, and probability density 2. And I like to look at that path and introduce an indicator for tipping. Okay. So from now on, everything is deterministic, but in the infinite dimension. Okay. So this is going to be involving with optimal control and the calculus of variation. And this is the picture that I showed with you, and I learned this from a number of people, especially people listed here about the Schrödinger bridge. Its setup and its properties. We developed the numerical codes as well. So there's something closely related to this. Is the on-Zag matching up action functional business in statistical mechanics. And it's a special case. I see this as a special case of Schrödinger bridge because it connects 2 points, 2 metastable points, which may be regarded as 2 delta probability distributions. So this has been used in our group to look at the transition as well. But now for the Schrödinger bridge, I already mentioned briefly, this is related to minimizing the KL divergence, which is also called relative entropy, given a reference probability density R here. For example, a reference measure may be the measure related to maybe just a Gaussian measure. We like to minimize it in an appropriate set. Okay. Relative entropy, also called a Kullback-Leibler divergence. Divergence means discrepancy. It's not a distance, but it tells us also about the relation between the two. But actually, it's the relative entropy. So this has some principles in there. So the Schrödinger bridge is minimizing the relative entropy. Okay, the minimizer is called Schrödinger bridge. The minimization is in a Wasserstein space of probability densities. So it's going to be a curve from 0 to capital T. It's a constrained optimal control. So that's why we're going to use Hamilton-Jacobi Bellman equation. Now the Wasserstein distance I mentioned is defined by this, but we're working on a p equals to 2. But this is also related to the optimal transport and other things. Yeah. So we have the Fock-Planck equation in this space. So Fock-Planck equation is a linear equation in this Wasserstein space, and it's a kind of a continuity equation because it's also called a transport equation. It transports the probability density. It transports the medical images from 0 to capital T. Now this auto magic, it involves with the theoretical part, but will not be useful for what we are going to do numerically. So this is in Ferrari's work, and so how to formulate this problem? This has been going on, at least this is related to Hans Former's work in 1988, we learned. So this Schrödinger bridge problem is calculus of variation. You have the Euler-Lagrange equation. But this Euler-Lagrange equation is hard to work on. So people will formulate it in different ways so that it's more tractable. One way is to use the coupled Kolmogorov equation. One is forward, one is backward. And then you multiply the two, you get the Schrödinger bridge. So this is one way to compute the Schrödinger bridge. One way to do the theoretical analysis. This has been going on for the last at least the last 20 years or so, especially for the last 10 years, motivated by the machine learning, diffusive generative AI. So this is one formulation. The second formulation that I personally like a little more because it involves the Hamilton-Jacobi equation. So again, you work on the Euler-Lagrange equation for the minimizer. we formulate it. You have a Fock-Planck equation with a Hamilton-Jacobi equation because it's optimal transport. And there are other formulations as well. This formulation is a coupled Hamiltonian system in the Wasserstein space. But this way use autocalculus. So this is the more theoretical stuff here. So and there are some theoretical work on this as well. So there are 3 formulations for the Schrödinger bridge. We choose one to do the calculation. Okay. So now if the noise is non-local, this story has not been finished yet. So this is something that we need to work on. Okay. Now for the rest of the 3 minutes, I'm going to talk about the computing the Schrödinger bridge and then introduce the indicator. This is related to the generative AI. Okay. This is done by Jinqiao in Wuhan, China. So we are going to compute the Schrödinger bridge as a transition path. And then we are going to compute the indicator, which indicates a critical transition. This is coming from this book, this paper. So this is a data from an ADNI data set. It's a set of images for the brain. Okay. Now this is for health brain. This is for the AD disease. So we like to find the Schrödinger bridge to find the optimal law connecting the both. Then we use this for the future prediction or early warning. Okay, good. So we use this. We use some basically machine learning to compute this. So there's a loss function, and this has been the computing Schrödinger bridge has been going on for quite some time. Now we have a curve, but this curve is infinite dimension. It's hard to sketch. But if the slope is a curve, so the slope or curvature, these are the geometrical quantities that we examine. So if the slope tilts to 45 degrees, then that's the tipping point for the so this is by looking at the slope. If its slope is bigger than 45 degrees, which means the slope is 1, right? Then that's the tipping board line. Now, how to compute that indicator? I mean indicator. We compute the energy. Now this V. Now the Fock-Planck equation will not drive the solution, will not drive the probability density from one state to another. So the optimal control will do the trick. That means you impose a velocity field or drift in the underlying stochastic system. So there is an underlying velocity. I don't have a better name for this. So there's maybe we call this Schrödinger velocity, because the optical control will bring the system to the second one. So this is the implicit energy. In fact, we can, by examining this velocity V, you pretty much know how the system is going. For example, I examine the kinetic energy. So this is the 2 good and bad initial and the terminal probability density, and then this is the evolution at the different time steps. This is that indicator function, like a thermometer, but this is kinetic energy. So it has pumps, so the slope increases. So that gives us the tipping point. This is the loss function in the machine learning. So it drops, so it sort of safeguard our computation. So this gives us a way to tell at what time you need to, for this specific data set, you need to look at the tipping or do something precaution. So thank you very much for your attention.
Okay, thank you, Jinqiao. So any questions from the audience?
Yeah, thank you. I'm curious in the slide just before. There are two like local maxima
Yeah.
in the action.
Yeah.
Why is that? That feels.
Oh, for this, there are 2, right? This one, yeah. So this is the indicator which we take as kinetic energy. So we compute the first one. Which one? Yeah, we use the first one. You want to. This is time, right? Yeah. So you use the first one as the early warning. Yeah. Also, it may not be the biggest jumping or tilting. Yeah, do as early as possible.
I was curious, do you know what the dynamic would look like for a healthy brain?
Dynamic is for what? For health? Oh, for health. That's a good question, right? So that means in that case we don't have to take any medicine. So so this basically means we have with for the same person the data set, you have a good image, a bad image 10 years later. So basically we are looking for trying to find the underlying medical law to govern this. Now if the two images are the same, then there will be no Schrödinger bridge. There will be just a straight line to connect the two pictures. So then there's nothing to do. Is it going to be a straight line? That's a good question, right? For our kinetic energy. So the kinetic energy, that's a good question. If these two pictures are Gaussian, there's a clear exact formula for the Schrödinger bridge. Now for the biometric, for this case, this may not be Gaussian, just two pictures identical. Then what will be the Schrödinger bridge? So the kinetic energy will not change. So I think it will be a kinetic energy. Yeah.
First one is the easiest. So what do you plot there on the axis in the top block?
But yeah. For this top one.
Yeah.
So this is the image, but is the do you know this T is yeah, the TSE.
Okay, so basically then you answer one of my questions. That means
Okay.
you take the image,
Yeah.
you do some dimensional reduction,
Yeah.
and then the probabilities over that dimensional reduction.
Right.
Quantity.
Developed by Jeffrey Hinton. Yeah, popular. Yeah.
Now, second questions. What is the relation of your alpha in the alpha process to any of this?
Okay. What's the meaning of alpha?
Yeah, what do you use it for any of
Good. Okay, for evaluation, that's we are working on it. But I mentioned a challenge here. Yeah, here. This one theoretic. This one is theoretic part is
the theory, but the applications
application for the Gaussian noise.
for the imaging.
For the imaging, yeah.
Yes.
Okay.
How is that related to this?
This is because this is a part of the Schrödinger bridge setup. So it's part of the Schrödinger setup. That means we have for example, if you use the Fokker-Planck and the HGB formulation, then in the FGB it uses that autocalculus. Now, if you use the forward and backwards formulation, you won't use this one, but still the alpha is there, is in the generator.
So you're saying that when you say you use the generative AI
Yeah.
to solve this problem, somewhere in the equation you solve this alpha stability process or not at all?
Oh, okay. For this application, we use the alpha forward backward. Yeah, we do that. Yeah, you do that. Yeah. Yeah, but I think your question, your real question could be or should be is, does this do something better compared with it? I have not got that part yet. Okay.
They're mathematical, they're practical.
Yeah.
Right. So now when you say you do generative model here, what exactly are you doing? Are you using the score-based diffusion model?
Oh, okay. Okay. Right. We have a method. Because for this one we just introduced the loss function, and not a very complicated AI for this one yet. Yeah. So yeah, but it won't matter whether the Gaussian or non-Gaussian. It's the impact that we want to know. So for this one we use the loss function that here is different. You want to have constraints here. Yeah. So the loss function has to take those two constraints into account. Yeah. Yeah. So for the AI part, we have not to do much innovation for that part. Just use what we have now available. Yeah. But if we like to do a full non-Gaussian analysis of this, then there will be some theoretical obstacles at this time. Yeah.
Any more questions from Jinqiao? If not, thank you very much.